Building media applications today requires pushing hundreds of video files through high-scale, automated processing pipelines every hour. ffmpeg is the cross-platform library that handles the encoding, muxing, and filtering for the majority of these applications. But configuring that library exposes a massive point of friction for engineers, discovering and validating the exact string of characters needed to make a command execute properly. The official ffmpeg documentation reads like a dense academic thesis, making it difficult to parse for practical, everyday implementation. Developers inevitably abandon the official manual and resort to scouring decade-old StackOverflow threads, hoping someone else has already solved their specific edge case. Relying on those outdated forums introduces minor syntax errors into production code, causing media pipelines to crash and forcing developers into hours of trial-and-error debugging. Building video automation hits a wall when developers cannot quickly translate an intended edit into ffmpeg's archaic syntax. Resolving this bottleneck requires moving away from chaotic forums towards structured, open-source solutions. This brings us to a specific GitHub repository, rendi-api/ffmpeg-cheatsheet. Rather than listing basic encoding commands, this document provides complex, validated filter graphs designed for production environments. Every command is categorized by the specific automation task it solves, from dynamic cropping to advanced asset generation. Integrating these pre-vetted modules into an engineering stack makes ffmpeg operations predictable and repeatable. The modern reflex for writing code is to open an AI chatbot and ask it to generate the script. But if you ask an LLM to write a multi-input ffmpeg filter graph, it will likely hallucinate flags that do not exist in the software. Standard AI models fail here because their training data lacks a concentrated, accurate set of updated ffmpeg edge cases to draw from. The cheat sheet solves this problem by acting as a machine-readable context bridge. The entire document is formatted as raw, heavily commented markdown, specifically structured for machine parsing. By feeding the raw.md file directly into an AI agent or an MCP server prompt, you supply the system with a validated reference text. This explicit constraint forces the AI to construct outputs using only the verified syntax and logic found within the document. In machine learning terms, this context injection technique operates as a retrieval-augmented generation, or RAG, payload. The repository provides the grounding necessary to turn an LLM into a reliable generator for complex video processing. To see the practical value of this context, look at how the repository handles the varying aspect ratios of user-uploaded files. An automated pipeline must take various video orientations and force them into a single standardized resolution before encoding. The cheat sheet documents a precise filter chain for this, beginning with the force original aspect ratio command flag. This logic calculates the dimensions needed to shrink the oversized input video to fit within the target frame, preserving the original proportions. Shrinking the video creates gaps. The pipeline must solve the geometry problem of filling empty space created by the downscale. The solution is a dynamic padding equation, output width minus input width divided by 2, mapped against output height minus input height divided by 2. By calculating the difference between the target frame and the new video dimensions, this formula identifies the exact coordinates required to perfectly center the video. These geometry expressions allow the same pipeline to process a range of incoming media ratios without manual intervention. The logic gets even more intricate when pivoting from visual geometry to automated audio routing. Managing multiple streams requires the map command, an operation notorious for causing silent errors that leave exported videos entirely muted. This diagram showing two overlapping sound waveforms on a timeline demonstrates the cheat sheet solution for blending tracks using the crossfade command. A standard linear crossfade often results in an unnatural drop in volume at the midpoint of the transition, or occasionally digital clipping. To prevent this, ffmpeg allows assigning distinct mathematical curves to govern the fade rate. The cheat sheet specifies an x, or exponential, curve for the outgoing track. It then counters this with a q-sin, or quarter sine wave, to ease in the incoming track. Applying these specific decay algorithms ensures that the crossfade remains audibly seamless and broadcast ready, requiring zero manual oversight. Pulling back from the syntax level, we must evaluate where this repository sits within a complete software engineering stack. For all its utility, the tool possesses a specific architectural limitation. It is a static markdown reference file, not an active program. You cannot run it directly as a CLI tool, and it does not operate as a programmatic wrapper library like ffmpeg-Python. The cheat sheet provides the instructions for processing media, but the engineering team still bears the responsibility of building the surrounding server infrastructure to execute them. By treating documentation as machine-readable context, developers can outsource the most tedious and fragile component of media engineering. Curating high-fidelity context, like this repository, allows developers to offload the complexities of archaic syntax to automated tools. If you want to stay ahead of the tools redefining how software is built, hit subscribe. To see how these automated logic principles scale into massive video systems, click the video on screen for a full breakdown of hyperframes.